Hi, my name is Snover. This is a video that I've made on breadth first search algorithm. This is a pretty useful algorithm. It's used for a lot of different very technical things such as serializing and deserializing data, understanding how packets can travel through networks with the least amount of jumps. And basically it's used in any kind of node system where the network understands who its neighbors are, and it needs to trace a path from one node to another node, and it needs to take the fastest path. So how does it work? Breadth first search algorithm, it traces paths and stores the paths, and it traces the path from any cell. And so a quick overview, basically each one of these nodes, you can see the arrow pointing to another node. These are all of its neighbors, but the arrows are indicating that it is a direction to travel. So if you wanted to get to A from any of these points, you would know where to get there simply by following the arrows. So the first thing that I'm going to do is I'm going to explain the types of data that we're going to be using. We're going to be using lists, queues, and a graph system. We'll be using a node graph in this situation, but it could be various types of graphs, like perhaps a hexagonal grid where you're trying to trace through the grid, like a player's movement or something like that. This is just going to be a conceptual system like this one, that knows its neighbors and is essentially a map of nodes. So we are going to be using three different data types. We're going to be using that grid, the graph, and we're also going to be using a list, and we're going to be using a queue. So the queue data type is basically the same thing as a list. A list is an item, list of items that we can retain information inside of. You can basically think of it like a bucket of items, but usually a list is, it can be sorted or arranged in different orders. A queue specifically is like a line, like a waiting line, like you would find at like a typical diner or something like that. Basically the first person there is going to be the first person served. And that's the same situation for our queue data type. The first item in is going to be the first item served to us when we need information from our queue. So our process. So we are going to start with the first cell, our destination. Whatever destination you're trying to get to is going to be where we are starting in this algorithm. We're going to add it to the queue, and that will trigger our algorithm because our algorithm is going to run while our queue is not empty. So basically we're going to say while we still have data that we need to process and sort through and figure out what the fastest path back is from this cell, while that list of items that we need to do that to is not empty, we're going to continue to pull items out of that list queue. We will then request each of the neighbors of that cell, and we will tell each of those neighbors that this cell that we are in right now is the cell that they would need to return to if we were in that cell. So again, I'll reiterate, when we're going through each neighbor, essentially what we're doing, if you want to visualize it, you can think of we're in one cell and we're looking out at all of the neighboring cells that are connected to that cell. When we look at all of the neighbors that are connected to that cell, we tell each of the neighbors that the return path to wherever we're trying to get to is the cell that we're coming from. And then we add each of those neighbors to our queue of data that we want to process in the same manner that we processed this one. So if you could think about it, what we would essentially be doing is we would be asking each one of the neighbors, we'd be asking for each neighbor, then we would be telling the neighbor to store the cell that we're coming from. And then for each of those neighbors, we're going to be doing the same thing to their neighbors. So as you can see, we'll actually be expanding outward from neighbor to the neighbor's neighbors to the neighbor's neighbor's neighbors. And essentially, each one we reach, we're going to put it into our list, which is going to be our processed list. And what that does essentially is we don't want to keep processing cells if we've already reached them. So once we've reached them, we want to put them into our reached list, our processed list, so that if they happen to be a neighbor of another neighbor, we don't want to go back in and reassign that value, especially later on in the algorithm. If that neighbor is a neighbor of another cell that's like finishing the algorithm and it just happens to be at the end, but that cell already has a really fast way to go back to the other. We don't want to visit it again. Once we've visited a cell and we've told that neighbor of that neighbor of that neighbor's neighbor, or some depth of the algorithm, we want to stop there and let that cell keep its stored neighbor. Also, if we weren't to do that, we would end up infinitely looping through this algorithm. This video was made with the intention of displaying an abstract overview of the breadth-first search algorithm. It was not meant to be necessarily a implementation of the algorithm, but merely an overview or an abstract of the algorithm itself to get an idea of how this algorithm works. I really hope this video helped give an understanding of this algorithm and how it works. I will go ahead and leave a small clip at the end which will time-lapse through the algorithm, and hopefully that provides some more insight about how this algorithm works.